Now we're going to look at a little bit more complicated problem, this one involving tension. So we have Mr. Russo standing on the edge of a perfectly frictionless cliff, because, you know, we have those in the world. We're just going to go ahead and pretend the edge of the cliff is ice here. We'll draw some nice ice going on. And on the edge of the cliff is a pulley. So Mr. Russo is standing here, and he's holding a rope. Rope is going over the pulley, and at the end of the rope is a bucket. And he's going to be sliding like that. And we want to know the acceleration across the cliff. Well, the key thing here is the fact that because my two objects, Mr. Russo and the bucket, are tied together, their acceleration is going to be linked, right? And that tension is going to be what sort of links those two together. In order to solve this question, we need to first draw a free body diagram for each of the objects we're interested in. We're interested in Mr. Russo, and we're interested in the bucket. So we're going to do Mr. Russo's first. All right, and as you know, all of my free body diagrams are a box. So here's my lovely Mr. Russo in a box. We see the fact that he is on Earth, so he has a weight, right? And that R does stand for the weight of Russo. He has a normal force, which is supporting him upwards. And then we have the force of tension from the rope, which is pulling him across. We do have acceleration in this direction, and we're going to go ahead and say that the positive x is to the right. All right, so I've got lots of little labels going on here that are sort of telling me about what's going on with Mr. Russo. Then we're going to look at the bucket. All right. With the bucket, we get a little bit more simplified diagram because there's not much going on with the bucket. The bucket is on Earth. It has weight, force of weight of the bucket, and it's also being supported by the rope. All right, so it has tension upwards. My bucket is accelerating downwards, and we're going to go ahead and keep to convention and say that up is positive. Excuse me, just sneeze. My bad. So, using these, we're now going to build equations that are going to help us solve for acceleration. As a part of that, we're going to apply Newton's second law to each case. We will start first with Mr. Russo's case. When we look at this, we're not really interested in what's going on in the vertical direction. It's going to cancel out. We don't really have any up and down acceleration. All of our acceleration is happening across. So that's what we're interested in. So the sum of my forces here is equal to the mass of Mr. Russo times the acceleration. Right? And the acceleration for Russo and the bucket is going to be the same. So my acceleration here is in the positive direction, so I need to make no changes to my right-hand side of my equation. I do need to go ahead and substitute what are my forces on my left-hand side. Well, in the x direction, it's only the tension. So the tension is equal to the mass of Mr. Russo times his acceleration. Well, we can't do anything else with this because we don't have tension. So we can't solve for acceleration here. We now need to go ahead and shift gears to find, apply Newton's second law to our bucket. So we're going to still look at the sum of the forces is equal to the mass of the bucket times the acceleration. Again, that same acceleration because my objects are tied together. Now we need to go ahead and sort of plug in some of my forces on the left-hand side. So I have my tension, which is up, so that's positive, and the force of weight of the bucket, which is down, making this term negative. All right, remember the signs do come from the direction the force is pointing in. The signs come from the direction the force is pointing in. So that takes care, whoops, sorry, my whole screen moved. That takes care of the left-hand side of my equation. The right-hand side does require a bit of adjustment. Because my acceleration is down, that's in the negative direction. So my whole side on the left becomes negative. Because my acceleration is down, my whole right-hand side becomes negative. All right, so we are ultimately going to find the acceleration of our system, of Mr. Russo attached to the bucket. But we have some pieces that don't really match. That's the tension. All right. However, we know from the rules about tension that both sides of the rope are going to have the same value. So if I solve this equation for t, I can now set these two equal to each other because the tension that Mr. Russo experiences has to be the same tension that the bucket experiences. So when I set these two tensions together, Mr. Russo times the acceleration is equal to the force of weight of the bucket minus the mass of the bucket times the acceleration. Our goal here, remember, is to get the acceleration. So we need to put all those like terms together on the same side. I'm going to add this term on both sides. So the mass of Mr. Russo times the acceleration plus the mass of the bucket times the acceleration is equal to the force of weight of the bucket. Remember, force of weight is equal to mass times gravity. So force of weight of bucket is going to be the mass of the bucket times gravity. So I am going to go ahead and sort of shift that in there. All right. So now I have A in both of these terms. I'm going to factor that out. So I have A times the mass of Mr. Russo. Let me fix that. My handwriting is awful. Mass of Mr. Russo plus the mass of the bucket is equal to the mass of the bucket times gravity. Remember, we're getting A by itself, so we're going to divide this term off to the other side. So my acceleration is equal to the mass of the bucket times gravity divided by the sum of my masses. All right. Now this equation is in terms of all of the variables we know. We know the mass of the bucket, that's that 32 kilograms. We know gravity, it's on Earth, so 9.8 meters per second squared. We know the mass of Mr. Russo, it's at 75 kilograms. So now we get to do the easy part, which is the plug and chug. And we get an acceleration of 2.9 meters per second squared. So that is how quickly Mr. Russo is accelerating towards the edge of that cliff. Hopefully he stops in time, because it would be very, very sad if Mr. Russo fell off the cliff because he decided to hold onto a bucket.